This talk is a continuation of wastewater treatment and overview. In this talk, I would like to focus more on modification in conventional activated sludge process as well as some of the fixed film process that is normally used for domestic wastewater treatment. So, first reactor is oxidation ditch. So, the schematic diagram of oxidation ditch is shown in figure. And the operational aspects are more or less similar to activated sludge scheme. Here, no need to provide primary sedimentation facility. The pre-treated effluent can be directly loaded into aeration reactor. So, followed by a secondary settler. Here 50 to 150% of activated sludge should be recirculated back to reactor. The MLSS population maintained in oxidation ditch is normally in the range of 3000 to 4500 milligram per liter. The reaction should be operated at high solids retention time, normally in the range of 10 to 25 days. While implementing this technology for industrial effluent treatment, we can keep solids retention time up to 48 days. The hydraulic retention time may be in the range of 12 to 24 hours for conventional treatment. While implementing the same technology for industrial effluent treatment, the hydraulic retention time may be in the range of 1 to 2 days. Here at the downstream side of this facility, we have sludge dewatering facility. No need to provide anaerobic digester to stabilize the sludge that will be generated during biological activity. So, the reactor consists of oxidation ditch. Here cage rotors are provided here for oxygen transport purpose. The mixed liquor will be collected in secondary settler and part of 50 to 150% of the activated sludge is recirculated back to the reactor to maintain adequate MLSS population in the reactor. The clarified effluent from the secondary settler can be disposed into natural water courses or land environment after attaining BOD level of 20 milligram per liter, suspended solid concentration of 30 milligram per liter. In any case, the TDS level of the treated effluent should not be greater than 2100 milligram per liter. These are some of the water quality parameters we have to consider while disposing treated effluent into natural environment. So, this is the actual diagram of oxidation ditch. So, this is the reactor setup we have. Here we have cage rotors are provided here. At the downstream side, we have solid liquid separator. With the help of the solid liquid separator, we can segregate active microbial population from the reactor. So, this is another view we have. So, the cage rotors are provided here. So, the purpose of this cage rotors are for oxygen transport purpose. So, this is another view of oxidation ditch. This is a cage rotor is provided here, say endless ditch. So, this is the overall view of sewage treatment facility. By incorporating oxidation ditch as a secondary treatment units, here no need to provide primary clarifier. The pre-treated effluent can be directly loaded into biological system. Subsequently, we have secondary settler. With the help of this secondary settler, we can segregate biological mass. So, if we analyze the performance of oxidation ditch, here we are operating the reactor at high MLSS concentration. At the same time, the solids retention time is somehow high when compared to conventional ASP system. Here we are keeping solids retention time up to a maximum level of 20 days. Applying this technology for industrial application, we can keep solids retention time up to 48 days. So, by operating any biological system at high solids retention time, in addition to carbon oxidation, we can achieve nitrification. By retaining biological mass for longer duration, most of the sludge will enter into endogenous phase of respiration. So, sludge is partly stabilized. In addition to carbon oxidation, we can achieve nitrification. The partly stabilized sludge can be dewatered by providing dewatering facility at the downstream side of the reactor. This is a bioreactor normally provided for oxidation ditch. Subsequently, we have secondary settler. At the downstream side of secondary settler, we have solid liquid, we have sludge dewatering facility to remove solid from liquid phase. So, this is the aerial photograph of STP incorporating oxidation ditch as a secondary treatment facility. So, these are other downstream side of treatment. If you want to reuse the water for some domestic purpose, we have to disinfect the water by providing UV disinfection or ozonization or some other disinfection facility that is accommodated at the downstream side of secondary treatment facility. So, in addition to that, we need solid handling facility to remove solids from stabilized solids, because the sled will undergo partial stabilization by keeping solids for longer duration. In conventional system, we are keeping microbial mass only up to maximum level of 12 days. Here we are keeping 20 or even 25. From some industrial application, we are keeping microbial mass for 48 days. So, that is why we can partly stabilize the microbial mass. So, next activity is the fixed film process or biological system. So far we have discussed various configuration of suspended growth culture. So, suspended growth culture can be achieved by suspending microbial culture in a reactor. Classical examples for suspended growth culture are activated sludge process and oxidation ditch. In addition to that, we have aerated lagoon. In all these cases, the beneficial organisms are suspended in aqueous phase. So, these organisms will move here and there throughout the reactor. It will take substrate throughout the reactor. While designing configuration of oxidation ditch as well as activated sludge process, we have to keep enough turbulence to avoid concentration gradient along space. But here the fixed film process or the biofilm process is entirely different from suspended growth culture. In what are the major benefits of biofilm process or attached growth culture? Here biomass hold up is high. In conventional ASP system, whatever biomass generated, that will be collected in secondary clarifier, part of the biomass is recirculated back to the reactor. Here the entire biomass is immobilized on the surface of the solid material. The excess biological mass will be wasted during sloughing process, but conventional ASP system biomass waste up is high. Here biomass hold up is more, because whatever biomass generated, that will be retained within the supporting material. The solids retention time is quite high when compared to conventional ASP system. Here the higher, by providing higher residence time of biological mass, definitely we can remove more mass when compared to conventional process like ASP system, but the removal efficiency of ASP is high. With respect to mass loading rate, if you operate your fixed film process in a better manner, definitely we can remove more mass when compared to conventional ASP system like activated sludge process. This is the formation of biological biofilm during in the case of immobilized growth process or trickling filter process. So, initially a thin some discrete biomass that will be generated. So, bacterial cell excretes some site of polymeric substance. That polymeric substance is called as glycocalyx. So, glycocalyx possesses excellent binding property. It also possesses an exchange property. Whatever trace nutrients required to support bacterial life, that will be retained there. If such nutrients are not available in bulk liquid, so these nutrients will be released by the strands that will be utilized by bacterial species. This is the peculiar advantages of this strand. So, another advantage of this polymeric substance is this polymeric substance will aggregate loose biomass that will be scattered in liquid phase, and the entire biomass will be adhered on the surface of the solid material. By immobilizing those solid material, we may get a growth like this. So, initially some loose aggregate will be formed. So, bacterial cell excrete certain kind of polymeric substance. With the help of this polymeric substance, the polymeric substance aggregate those discrete biomass, and a colony will be formed. Later on, a thin biological layer will be formed around the surface of the solid materials. This is some photograph of biological film formation. This is a bacterium single cell. This is the flagellus. This is another bacteria is displayed here. So, this is a photograph of scanning electron microscopy. With the help of this same picture, we can see the external morphology of the bacterial cell. So, these are the bacterial cell, these are the strands, these are the polymeric substance glycocalyx that will be excreted product. With the help of this polymeric product, they can bind the cell and it can be cemented on the surface of the solid material. I already pointed out, with the help of this polymeric substance, we can retain the trace nutrients required for the bacterial cells, because in addition to the major macronutrients, bacteria require some of the micronutrients. Sometimes these micronutrients are not available in feed stream. So, these nutrients that will be already captured there, that will be released as and when bacteria require those trace nutrients. This is another photograph of biological cell that will be forming during immobilization process. The important reactors are rotating biological contactor is a dynamic reactor. Another configuration we have trickling filter, biological contact oxidation is a biological filter. So, this is a configuration of trickling filter. So, trickling filter consists of a solid material. Here, so we need a packing media. The wastewater is to be treated, is fed onto the top surface of the reactor. It can be evenly spread throughout the surface by providing distributor arm. So, this is the distributor arm. The primary clarified effluent is fed to the reactor on the top surface. It can be evenly circulated on the surface by providing distributor arm. The percolate can be collected at the bottom of the reactor. This is the rotating biological conductor. 40 to 60% of the media surface is immersed in water. Rest of the media surface is exposed to atmospheric air. When the media surface is exposed to atmospheric air, the atmospheric oxygen try to diffuse into liquid film, then into biological film. When the same surface is again immersed in water, whatever oxygen already transported when the surface is exposed to atmospheric air, that will be released in bulk fluid. So, by this way the system is continuously aerated. So, this is the aerial view of a trickling filter using conventional packing as a packing material, is a packed bed reactor. So, this is a reactor with stone as a packing media, is a low rate trickling filter. With the help of this trickling filter, we can load up to 420 gram BOD per meter cube per day. We can pack the media up to a maximum height of 2 or even 2.5 is possible if we provide some ventilating port on the depth of the reactor. So, up to 2.5 meter, the reactor will maintain aerobic air condition. So, if we want to pack more than 2.5 meter, then we have to modify the media package. So, this is a conventional media, stone media is used as a trickling filter media. Is another reactor using random plastic as a packing media. Is another reactor using random plastic as a packing media, is a synthetic media. So, another view here. So, this is a conventional one using stone as a packing media. Here is a modular sheet is used as a packing media. With the help of this modular sheet plastic media, definitely we can load up to 1 kg BOD per meter cube per day. With the help of conventional media, we can load up to 420 or even 460 gram BOD per meter cube per day, but the hydraulic loading is less than 4 meter cube per meter square per day. If you incorporate modular sheet plastic as a supporting material for bacterial growth, so definitely we can load up to 40 meter cube of water per meter square area per day. So, that the hydraulic loading is much more. In addition to that, we can load up to 1 kg BOD per meter 1 kg BOD per meter cube per day. So, loading rate with respect to hydraulic aspects as well as organic loading is quite high when compared to low rate trickling filter, because what is the reason behind this loading is, so if you provide modular sheet as a packing media, we can provide more void space. So, only less than 5% solid media, remaining 95% void space. So, void space will definitely promote oxygen transfer. Here the oxygen transfer is by natural mechanism. Whatever oxygen trapped in between pore space will diffuse into liquid layer because of the DO deficit in bulk fluid. So, here in between pore space as well as outdoor atmosphere, oxygen transport is due to partial pressure gradient, because if you investigate the oxygen concentration of pore space of the packing media, the outdoor atmospheric condition, if you investigate the performance with respect to outdoor atmosphere, a partial pressure gradient will be established in between pore space of the packing media as well as the atmospheric air. So, the driving force responsible for migration of oxygen from atmospheric air to pore space of the packing media is a partial pressure gradient. Once oxygen reaches the pore space, then further migration towards the biological film is due to DO deficit in bulk fluid. So, this is the relative force or the relative rate of mass transfer from pore space to bulk fluid is related to DO deficit in bulk fluid. So, deficit is quite high here. So, once oxygen is transported into bulk fluid, further migration occur because of concentration gradient within the liquid film. So, once reaches the liquid film, then into biological film. In biological film, plenty of bacteria, billion number of bacteria are residing there. They require molecular oxygen as a terminal electron acceptor. Whatever oxygen as well as substrate that will be transported by diffusive mechanism, that will be captured by aerobic bacteria for their survival as well as a terminal electron acceptor. Ultimately, the organic contaminants are converted into carbon dioxide and other end products. The end products are released in the form of gaseous state that will come out from liquid to gas by natural mass transfer phenomena. So, transport is a major phenomena that will be accounted while designing configuration of trickling filters as well as other fixed film process. Here the rate of overall reaction rate is controlled by mass transfer mechanism. So, diffusion is the predominant, this diffusion is a limiting factor in most of the reactor design, because that rate transport is a major step in biological process design. Any biological system, the relative rate of mass removal is related to rate at which the organic matter entering into the system, rate at which oxygen transported into biological film. Here the rate transport is by diffusive mechanism only. Diffusion cannot be aggravated here, because that whatever oxygen transported, that is by natural mechanism only. So, this is the aerial view of trickling filter. This is another solid, this is a supporting material that is provided at the bed of the reactor to collect the percolated effluent. So, trickling filter is a three phase reactor: liquid film, solid phase is there, as well as biological film is there. This is a configuration of modular sheet plastic media, is a vertical type of configuration we have. This is a cross flow configuration. Here we are trying to create certain disturbance by distributing flow in such a fashion. By this way, we can definitely enhance the transport. I already pointed out any transport phenomena that can be aggravated by creating slight disturbance in bulk fluid. By creating slight disturbance while allowing liquid to pass through the packing media, definitely we can transport more quantity of substrate from bulk fluid to biological film. At the same time, we can indirectly accelerate the oxygen transport phenomena. Any transport phenomena, turbulence will definitely enhance its performance. Here, by spreading water into larger area, by spreading water into packing media, we are splitting as well as joining flow at each nodal point. So, this will definitely create some sort of mixing while admitting water to pass through the packing media. So, this is a peculiar advantage of cross flow media when compared to other flow pattern like vertical flow, wavy flow, as well as spiral flow. So, with the help of this definition sketch, we can understand the working principle of trickling filter. So, trickling filter consists of a solid material. It can be plastic or conventional one. The wastewater is to be treated is sprinkled on the top surface of the reactor by providing distributor plates. The percolate can be collected from the bottommost surface of the reactor by providing under drainage facility at the bed of the reactor. If we sprinkle wastewater on the top surface of the reactor, a thin biological layer will be formed around the surface of the solid material. The mechanism I already pointed out here. So, this is a diagram here. The blue shade represents the water film, liquid film. This is a biological film. So, whatever organic matter present in liquid layer will diffuse into biological film by diffusion phenomena. If any solid particles are there, if any polysaccharides are present in effluent stream, that will be converted into soluble matter by enzyme mediated transformation, because bacteria can observe only organic matter in soluble state only. The insoluble organic matter will be converted into soluble one by hydrolytic enzymes. So, during enzyme mediated transformation, the polysaccharides are converted into monosaccharides that can easily diffuse into bacterial cell wall. So, in order to maintain aerobic activity, we have to provide adequate quantity of DO. So, oxygen present in pore space will diffuse into biological layer. So, if we investigate the performance of pore space with respect to atmospheric air, here a partial pressure gradient is established. That is why continuous mass transfer will occur because of the partial pressure gradient in between pore space as well as atmospheric air. So, once oxygen reaches here, the organism present very close to media surface utilize whatever oxygen diffuse into biological layer. So, those organism or those microbial community residing very close to media surface may not get adequate quantity of oxygen for their metabolic activity. So, this organism entering into endogenous phase of decay. So, this organism will enter into death phase. At the same time, the organic carbon available here may not diffuse into inner layer. So, this organism will enter into death and death phase. The entire structure will be detached from the media surface. That activity is called as sloughing. So, by this sloughing way we can control the excess growth, otherwise growth can be prevented. The growth is a continuous phase if you operate your reactor in a continuous manner. So, in order to control the growth, we have to consider organic loading rate as well as hydraulic loading rate at appropriate level for continuous sloughing of the media. By this way we can maintain active microbial film thickness for better transport phenomena as well as better BOD removal. This is a mixed media. So, we can integrate various packing media. This is the top surface of trickling filter configuration. So, another reactor is rotating biological contactor. So, trickling filter is a stationary reactor. There the solid materials are packed there. Here rotating biological contactor is a rotating one. So, 40 to 50% of the media surface is immersed in water, rest of the media surface is exposed to atmospheric air. This is a photograph we have. The microbial colonies are adhered on the surface of the rotating disc. So, this is a schematic diagram of rotating biological contactor. So, if you want to implement this technology in wastewater treatment facility, so we have to provide primary settling facility followed by biological reactor. Some cases primary treatment is not required. The suspended solids are more, in that situation only we can incorporate primary settling. Okay. Normally that primary settling can be avoided for extended aeration system. Rotating biological conductors, in order to minimize load entering into secondary treatment facility, definitely we can have primary settler. So, at the downstream we have rotating biological contactors, we have 3 different configuration of RBC in sequence. So, at the downstream side we have a secondary settler, that purpose is to segregate biological mass. Here no need to recirculate biological mass, but in conventional activated sludge process we have to recirculate part of the microbial community. Here no need to recirculate anything. So, this is another one is a moving bed biofilm reactor. Here we are trying to integrate the benefits of suspended growth culture as well as attached growth culture. So, integrating these two activity, definitely we can get a better mass transfer rate. For the purpose we can use this polythene media. This is a lighter media, the specific gravity is very close to 0.95. This is a lab scale reactor to investigate the performance of MBBR. So, primary settler followed by secondary settler. So, lab scale reactors are normally used to investigate the performance, or if you want to study the performance of any real scale reactor, we have to fabricate some kind of lab scale reactor to investigate this transport phenomena as well as kinetics. All other aspects can be definitely studied with the help of this system. Here this is the experimental setup we have. So, this, I think the configuration of the reactor is moving bed biofilm reactor. So far we have discussed various configuration of suspended growth culture. The major configurations are activated sludge process and oxidation ditch. The major difference between oxidation ditch as well as conventional ASP systems are, in oxidation ditch we are trying to nitrify the effluent. In addition to that, we are trying to stabilize the sludge in partial manner. By this way, no need to incorporate anaerobic digester at the downstream side. Here, if we consider oxidation ditch as a secondary treatment system, no need to provide primary clarifier. The pre-treated effluent can be directly loaded into the reactor. Subsequently, we no need to attach any anaerobic digester to stabilize the sludge, because the sludge is partly stabilized. So, another system we have discussed so far is fixed film process or biofilm process. The major reactors are trickling filter and rotating biological contactor. So, next we are going to discuss the various configuration of natural based treatment systems like waste stabilization pond. So, waste stabilization pond is working on natural mechanism. The pond, based on the reactor performance or the loading facility, we can categorize reactors into anaerobic reactor, facultative, maturation pond as well as aerobic reactor. So, first one is a facultative type of pond. Here in multiple ponds we have 3 different ponds in sequence. One is anaerobic pond, so followed by facultative pond. At the downstream we have maturation pond that will act as a polishing one. Here 3 different facultative ponds are connected in parallel. So, most of the stabilization ponds are working based on algal bacterial symbiotic action. So, algae produce oxygen during daytime. With the help of oxygen, bacteria can use oxygen as a terminal electron acceptor for microbial stabilization process. So, that can be illustrated with the help of this diagram. So, from this diagram, so during daytime with the help of light energy, algae can produce their own food material with the help of inorganic plant nutrients. These nutrients are released by bacteria during biological metabolism. So, during algal photosynthetic action, a huge quantity of oxygen will be liberated, that will be in dissolved state in bulk fluid. Whatever oxygen released during algal photosynthetic action, that will be utilized for aerobic bacteria as a terminal electron acceptor. The organic matter loaded into the reactor, that will serve as a substrate for aerobic bacteria. At the end of aerobic biodegradation activity, lot of cells are released during synthesis process. At the same time, the organic matter will be transformed into inorganic plant nutrients. Here carbon dioxide is liberated. The carbon dioxide will serve as a carbon source for algal species. Algae require nitrogen for their productivity. Here the nitrogen in ammoniacal form or in nitrate form will serve as a nitrogen source for algal species. At the same time, the phosphorus present in effluent stream of wastewater will be converted into phosphate that will serve as a phosphorus for algal species. So, algal species require carbon, nitrogen, phosphorus in inorganic form. In addition to that, they require some of inorganic micronutrients. So, all these nutrients are available in wastewater because during biological transformation, during bacterial transformation, the organic matter available in the pond will serve as a inorganic plant nutrient that will be converted in inorganic one. So, this is a schematic diagram of this reactor setup. In aerobic, this is a facultative pond. In facultative pond, in addition to aerobic bacteria, the bottommost region is anaerobic in nature. The anaerobic zone is fluctuating in nature. So, whatever wastewater loaded into the reactor, that will be converted into inorganic plant nutrients that will be assimilated by algae for their photosynthetic action. New algal cells are produced. So, during daytime, oxygen will be liberated. During night time, oxygen is used for their respiration phenomena. So, with the help of that, they can capture, they can utilize their energies already stored during photosynthetic action. The oxygen will serve as a terminal electron acceptor for bacterial species. Here the mass transfer is by, in addition to this oxygen transfer by algal photosynthetic action, some mass transfer will occur because of wind action as well as wave action of water. So, but if you investigate a DO level with respect to vertical direction, the DO level at the top surface of the system will be high during daytime. Gradually it decreases with respect to space because most of the algal species are present on the top surface of the reactor. If you want to keep your reactor in aerobic condition, the minimum depth to keep aerobic activity is up to 0.9 meter, sometimes it can be extended up to 1.1 meter. So, if you operate your aerobic pond at low loading as well as the depth is shallow in nature, the aerobic bacteria are predominant in our biological system. So, if you want to maintain facultative condition, we can increase the depth of the reactor up to 1.5 meter and slightly increase the BOD load. Top surface of the reactor will act as a aerobic pond. So, middle layer some facultative zone is there. So, bottommost region is anaerobic in nature because whatever suspended solids present in effluent stream will deposit at the bed of the reactor. The benthic organism present at the bottommost region will utilize the oxygen available in bulk phase. So, the bottommost region or the benthic region is devoid of oxygen. So, ultimately an anaerobic zone will be established at the bottommost reactor. So, if we investigate the performance of this anaerobic pond, we can find three different types of layer. One is aerobic layer, second one is the fluctuating layer, this is facultative zone. So, bottommost region is anaerobic zone because of the huge deposition of suspended matter present in effluent wastewater. So, top layer is strictly aerobic in nature because adequate quantity of oxygen will be liberated during photosynthetic action as well as wind action. So, oxygen liberated by photosynthetic action is high when compared to oxygen that will be naturally transported into bulk phase by natural transfer mechanism. So, the middle layer is facultative layer. So, facultative bacteria can survive in the presence or absence of oxygen. Even oxygen is there, they can tolerate. If there is no oxygen, this kind of bacteria tolerate. So, we can observe three different types of bacteria in a single reactor. So, top layer aerobic layer, they are obligate aerobes. So, middle layer is facultative bacteria, they can survive in the presence or absence of molecular oxygen. So, bottommost region, so entirely absence of oxygen. In that layer, in that benthic layer, most of the anaerobes are present there. So, during anaerobic activity, lot of gases will be liberated. Major gases are carbon dioxide, methane, hydrogen sulfate that will be added there. In addition to that, some nutrients are released during anaerobic activity. So, the nutrients will serve as a nutrient source for the algal species. In addition to that, facultative bacteria release some of the nutrients. So, whatever nutrients that will be liberated during aerobic or facultative or anaerobic activity, that will serve as a nutrient source for bacteria. By this way, these two organisms are mutually benefited. That mutual symbiotic action is called as algal bacterial symbiotic action. So, most of the algal ponds or the stabilization ponds are working based on algal bacterial symbiotic actions. Two species are present there. These two species are mutually benefited because of the symbiotic relationship. So, algae species release oxygen during photosynthetic action that will serve as an electron acceptor for aerobic bacteria. Aerobic bacteria convert organic matter present in effluent stream that will be converted into inorganic plant nutrients. These inorganic plant nutrients will serve as a nutrient source for algal species. So, this is a natural pond we have, the pond system. So, in order to protect the seepage of contaminated water, we have to provide proper lining. That is a major important aspect while designing configuration of waste stabilization pond. This is the proper, I think the reactor is properly lined by providing concrete liner. So far, we have discussed various configuration of natural pond system like waste stabilization pond, aerobic, facultative pond and anaerobic pond. So, anaerobic pond is the entire reactor is anaerobic reactor, the depth may be 2.5 to 4.5 meter. So, next setup is septic tank system. Septic tank is more popular in village area. With the help of this septic tank, we can remove the suspended solid present in wastewater. At the same time, some extent we can remove some of the organic matter present in wastewater. So, this is a schematic representation of septic tank system. The sewage that will be generated in domestic activity can be stored in septic tank. The effluent that will be released during treatment aspects that can be dispersed into larger area by constructing dispersion trench. So, dispersion trench is an important component in septic tank design. So, this is another setup we have. So, wastewater is collected from the septic tank and it will be collected in a holding chamber and it is finally dispersed into dispersion field by conducting drained like this. So, here we have PVC pipes with perforations, or it can be stoneware pipe without joints. So, in order to disperse effluent evenly throughout the soil, we have the entire setup is embedded in gravel pack assembly. So, gravel, perforated pipe and a gravel pack is there. So, this is the configuration of this is the configuration of septic tank. It is a single chamber. So, on the top surface, in order to relieve the gases that will be generated during anaerobic activity, we have to provide vent holes on the top surface of reactor. In order for desilting purpose, manhole is provided here. So, desilting operation frequency may be once in a year or once in 2 years, like that we have to remove the accumulated solid matter. The effluent or the wastewater that will be generated from the household can be stored here. In order to avoid turbulence while admitting wastewater into the reactor, we have to provide T type of entry pipe. So, by the pipe is elevated one. The purpose is to avoid entry of scum particle. So, this is the configuration here. In order to minimize the turbulence that will be generated while allowing wastewater here, we are providing this T type entry here. Here the clarified effluent can be collected from the reactor by providing T type outlet pipe that is provided at the outlet. Here is the floating matter, there is a scum matter that will be generated during anaerobic activity. So, if we investigate the performance of anaerobic system, 4 different organisms are interacting in anaerobic system. One is enzymes, they are hydrolytic enzymes most predominantly. Their role is to convert the polysaccharides into monosaccharides. So, these monomers can easily diffuse into bacterial cell wall. So, first type of organisms are acidogenic bacteria. Acidogens use this soluble organic matter into simple organic acid. Subsequently, one set of acetogenic bacteria, the acetogenic bacteria convert the higher organic acid into acetic acid. Then finally, 2 different groups of methanogenic bacteria are interacting. One is hydrogen utilizing methanogens, another one is acetate utilizing methanogenic bacteria. Ultimately, the hydrogen as well as acetate are converted into methane, carbon dioxide and other gases. So, at the end of anaerobic activity, the organic matter fed in the reactor will be converted into carbon dioxide, methane, hydrogen sulfide and other gases. So, in order to relieve those gases, we have to provide vent facility here. The suspended solid will deposit at the bed of the reactor, it will undergo anaerobic oxidation. In addition to that, the organic matter present in the feed stream will undergo stabilization. While designing configuration of the reactor, we have to provide 24 hours hydraulic retention time for while considering the volume of the reactor. In addition to that, desilting operation is once in a year or once in 2 years. So, another thing, the soluble matter, well, we have to provide enough space to accumulate solids, because the desilting operation is once in a year means. So, based on the solids generation date, we have to provide adequate space in addition to liquid storage volume. So, liquid storage volume can be quantified based on the detention time as well as rate of flow. If the system is designed for a community of 100 people, then based on the water supply rate, we can roughly quantify how much quantity of wastewater will be generated. As per CPHUO recommendation, roughly 80% of the water supply will reach as waste. So, we can quantify wastewater flow based on this simple calculation based on the per capita water supply for rural sub if they for village people. So, quantity of based on the quantity of water entering into the reactor, we can design the size of the reactor. In addition to that, we have to provide adequate space to accommodate stabilized sludge as well as raw sludge digestion, scum storage. These are the 4 components you have to consider while fixing volume of reactor, and adequate free space to be provided on the top surface of the reactor. So, liquid space, space for scum, space for anaerobic digestion of fresh sludge. The digested sludge should be stored here. So, all these 4 components to be integrated while designing geometry of the reactor. It is normally rectangular in shape. This is a 2-stage reactor. So, one is for exclusively for sedimentation, another stage is for anaerobic digestion. Here some sort of anaerobic digestion will occur. Instead of T-type arrangement, here we have baffle valves are there, here also baffles are there. To collect the clarified effluent, we need this configuration of baffle valve. This is 2 chambers are provided here. So, volume is here 2/3 of volume, this is rest of 1/3 volume is accumulated here. Here some ports are provided for to admit clarified effluent into subsequent reactor. So, most of the sludge will be collected in first stage reactor. Here some sludge will be generated during anaerobic decay, because if you investigate the performance of anaerobic system, only 5 to 10% of BOD will be transformed into biological solids. But if you investigate the performance of aerobic system, there roughly 50% of the input solid will be converted into biological matter. So, solid production is very less in anaerobic system, only 5 to 10% of the input solids are converted into biological solids during anaerobic transformation. That is why we need little bit of space to accommodate digested sludge within the reactor. So, while designing the first compartment, we have to provide adequate space to accommodate raw sludge, the influent suspended solid. Here the soluble organic matter entering into this reactor, whatever soluble organic matter present here, that will undergo anaerobic decay. So, at the end of anaerobic reactor, due to liquefaction as well as gasification, the organic contaminants are converted to the gas and liquid. The gas can be directly relieved into atmospheric air by providing ventilation ports. So, ventilation ports are provided here to relieve gases that will be generated during anaerobic decay. Once in a year or once in 2 years, we have to remove digested solids that will be accumulated within the reactor. So, this is a trench facility that we have already discussed. So, another aspect I would like to discuss is grey water harvesting. So, how to harvest grey water? So, grey water is a wastewater arising due to domestic activities. So, grey water is nothing but sewage minus waste from water cluster. So, how do you recover solvent from grey water? That aspect we are going to discuss here. So, grey water, this major sources of grey water from washing facility, dishwash, so bathing facility, all these 3 are all the waste from kitchen sink, then kitchen sink and the washing facility as well as bathtub are collected here in septic tank. At the downstream side, we can provide some sort of coarse filtration, so sand filter may be considered as a suitable option. So, in addition to that, if you want one more reactor as a coarse sand filter in a horizontal manner or vertical manner, one more reactor it can be sand filters of fine sand. By this way, we can connect 2 reactors in sequence to remove suspended particle present in the septic tank effluent. So, first reactor we may consider as a septic tank or a holding chamber. So, in order to collect wastewater from the reactor, some sort of settling will occur here, some anaerobic activity may be there in our septic tank. So, followed by filtration will occur in 2-stage or single stage reactor. Yes, 2-stage or single stage reactor. One is coarse sand filter followed by fine sand filter. So, ultimately if you want to polish the quality, then it can be reused for gardening purpose or other irrigation purpose. So far we have discussed various functional elements of wastewater treatment. So, first we have discussed the various advancement of conventional ASP system. So, typical example for advancement ASP system is oxidation ditch. Here we are trying to achieve nitrification by enhancing solids retention time, at the same time by holding wastewater for longer, by holding biomass for longer duration. In addition, here we are trying to achieve biological stabilization of the generated sludge that will be generated during aerobic respiration. So, if we consider oxidation ditch as a primary as a secondary treatment option for wastewater treatment, no need to provide anaerobic digester at the downstream side. In addition to that, In order to operate a reactor in an efficient manner, no need to incorporate primary settler. The pre-treated effluent can be directly loaded there. Then we have discussed the various aspects of fixed film process like trickling filter or rotating biological contactor. So, one of the major advantage of trickling filter is here we can hold biomass for longer duration. Here we are trying to immobilize microbial community on the surface of the solid material. By immobilizing microorganism on solid support material, we can provide more solids retention time rather than liquid retention time. The biomass can be wasted by sloughing activity. Here the hold up is high, it can withstand with load if you operate your reactor in a better manner. The oxygen transport is by natural transport mechanism, but one of the drawback of this system is we can attain maximum efficiency of 80 or 85%. So, if we consider conventional system as ASP, definitely we can achieve 95%. If we consider ASP as a major treatment option, as oxidation ditch as a major treatment option, so definitely we can achieve 98% efficiency. So, if you want to achieve stringent effluent quality standard as 20, then we should go for some mechanized treatment system like ASP or oxidation ditch, not trickling filter, because with the aid of trickling filter we can remove more mass at the transport as other aspects are somewhat high, but other thing as per the effluent point of view. So, we need some more polishing units that should be accommodated in our downstream side to attain stringent wastewater quality standard or stringent effluent quality standard. So, third system we have discussed some of the various aspects of natural based treatment system like waste stabilization pond. So, waste stabilization ponds are working based on the natural mechanism, algal bacterial symbiotic action. Then some aspects of septic tank we have discussed. Septic tank is a natural based treatment system. So, if you want to harvest grey water from household, then we have to incorporate some more reactor at the downstream side of septic tank followed by sand filter, then some polishing is required. So, if you want to reuse wastewater for flushing purpose, disinfection is mandatory. So, if you want to use grey water for gardening purpose, no need to incorporate disinfection facility, we can directly use water for gardening facilities. So, to this I would like to wind up this lecture. Thank you.